All right, class. We can get started. All right, so in today's class, no video. It will be the one day this week without videos. Yeah, well, we'll get back to them. Today we have do some ground to cover to finish up chapter 2 and get you ready for homework 2 will be assigned today. And so today we're going to talk about an example of what we can do with surface tension, problem we can solve with surface tension. We'll talk about how fluid density leads to forces within a fluid, and then we'll have an introduction to manometers and how manometers work. As another reminder, homework 1 is due today. This is the math review homework. So today by 11:59 p.m., right, so just before midnight. Do that so that the AM PM thing is on video, so no confusion of other new midnight. So homework 1 is due today. Now, as a reminder, I'll drop your 2 lowest homework scores in the class. This is probably the easiest. Homework 1 is probably the easiest. So you probably don't want this one to be one of your 2 dropped scores. So please get this one in time. And then yeah, homework 2. All right, any questions before we get started for today? Okay. All right. So last time we introduced the concept of surface tension and surface weigh. And we can use those concepts to solve this problem. Where we ask, what is the height of this column of water? Right. So this is a case where we have we take some like let's say this is so this is water and this could be glass. And we know that glass is weigh, meaning that liquid will tend to spread out. So that means we're going to get a viscous shape like this, where the angle at the top here, that theta, that's the contact angle. So that's the angle that defines the interaction between these 3 materials, right? We have, let's say, air, water, and glass. We'll define that contact angle. If we get to change any one of those 3 materials, what happens to contact angle? It changes. Right? It depends on all of them. But now, so if we take a small cylinder, let's say a flask, dip it in water, we'll see liquid rise up by a capillary. And we can now address the question of what is the height of this column of water. And so we're going to look at the case where the liquid has stopped moving, right? So we've reached steady state, and everything is in equilibrium, right, or force balance. And so we can basically solve a force balance for this fluid, where we're going to say that the force at the edge of the glass, the interface between the glass and the water. Right, there will be a surface tension force which is pulling this material upwards, pulling that water upwards. That's going to be balanced out by the weight of the fluid column. So we can write that out in math. Right, so the surface tension pulling up is balanced by the weight of the liquid pulling down. And remember, so if we're looking at this viscous here, right, we're going to have some surface tension force of small y that is so that coefficient of surface tension is force per unit length, and it is acting parallel to the surface of the water in this case, and we're going to be doing a similar force balance in this direction, right, in the vertical direction. And so we want the component of this surface tension force that's pulling upwards to be gamma times cosine of theta. So that's going to be our force for length pulling up. Right, so cosine theta times that epsilon. And we're going to multiply that times the circumference of the circle around which that force is acting. Right, so the water column is being held up by this ring of force, right? This ring of force at the edge of the cylinder. And that's balanced out. It's in equilibrium, right? Some of the forces are zero. It's balanced out by the mass times gravitational acceleration. Right? Here we're talking about the mass of this column of fluid that we're holding up. You can find that mass column of fluid as the density times the volume. Like this. Yep. So the density times volume pi r squared times h. And now we have an expression that we can use to solve for h, which is the height of the fluid column, which is the thing that we want to know. Right, so we just do some rearrangement, and we end up with h is 2 epsilon over rho g r times cosine theta. So we used what we know about surface tension to solve this fluid statics problem and answer the question of where, if we put a column or we put a tube into water, for example, how high does the column reach? Right, it depends critically, for example, on the radius of the tube. And this tells us something else as well, which is that the weight of the fluid can cause a force. And that's where we're going next. We already alluded to this a little bit, where we said that atmospheric pressure is the weight of the column of atmosphere that's above me. In this case, we're talking about the weight of this fluid column, right? And that gives rise to a force on the fluid. In this case, balanced out by surface tension at the column. So in general, when we have a force due to gravity, it gives rise to a pressure difference within the fluid. And the pressure between 2 points in the fluid of finite height, and this would can be written as delta P is equal to minus rho G delta Z. Right, so the difference in pressure between two elevations in the fluid given by Z minus rho G delta Z. Again, remember that negative sign, told you, warned you, it's going to be kicking around nearly every time we work with pressure forces. We have that negative sign from the central convention about pressure forces acting inwards. We're going to see these terms rho G appear together quite often when we're dealing with this kind of fluid statics type problems. And since we're also generally going to be doing this on Earth, right, where G is 9.81 meters per second squared, we're going to typically group these things to these two terms together. And say rho G is gamma in specific way. Gamma not to be confused with that epsilon or y looking thing that we use for the coefficient of surface tension. We're running out of letters in the alphabet, so we're turning to the Greek alphabet and starting to use one to get a little bit confused. But just don't get, make sure you don't mix those two up. So this would be the specific weights. In terms of newtons per meter squared, we can see some common specific weights of different fluids, so some air, 1.8 newtons per meter squared, water, 9,790 newtons per meter squared. And then you will sometimes see this written as specific gravity instead. So specific gravity is the ratio of gamma of your fluid to gamma of the water. Basically, an answer to the question of does it sink or float? It's the value of this gamma. And so if gamma is greater than 1, the fluid is more dense than water. If gamma is less than 1, the fluid is less dense. So oil will float. Water, seawater is heavier than burning water. And just pull that out. So this means that we can now, so we can take this expression and put it into a differential form if we want to find the distribution of pressure within a fluid at rest, within a static fluid. So basically, we're going to take the limits where the volumes, the deltas that we're considering get really, really small. So we can start talking about continuous variation in pressure within fluid. We get P dz is equal to minus. And note here, just to remember that the pressure gradient creates a surface force that acts at the surface of fluid elements, or came up in our derivation of the pressure gradient force on a fluid element. And in this case, we're showing that within the static fluid condition, the pressure gradient basically arises, the PVC arises to balance the body force, or a force that's exerted in the center of the fluid element, which is pressure. So this is another statement of force balance. This is what it did. When we derive the equations of fluid motion, we're also going to we're going to essentially force balance there. So we have this. Again, this surface force being balanced out by a body force, a force that's felt by throughout the fluid itself. In general, we're going to be considering variation in Cartesian coordinates x, y, and z. So we have PdZ is minus gamma, but in the fluid static condition, we would have no variation in pressure in x and y. So PdX equal to 0 and y. So what this means is that if we're considering the distribution, we want to know the distribution of pressure within a single fluid, we can integrate this. Right, so we now have a separable differential equation, and we can integrate this. Separable differential equation being something you'll see on one if you haven't already. So we can integrate this this expression and then use that to find the pressure within a fluid as a function of elevation. Basically bring it back to the discrete form that we had earlier. We're at P2 minus P1 is minus M of Z2 minus V1. So this is maybe in your notes, this is a good equation for the box and the star. This is one that you're going to be using all the time to solve problems in hydrostatics. Okay. We'll go through a little bit of this today with some examples and set up some problems, some manometer type problems that you're going to see on homework too. But you'll be using this very quite a bit. One thing to be careful about, and we'll hit on this again. So this negative sign, this is one of those places where the negative sign is going to become a little bit confusing. Just remember the order here: P2 minus P1 minus gamma Z2 minus Z1. Probably the most common mistake on solving these types of problems is flipping a sign somewhere in your deltas. And we'll look more practically at what this means and how we apply this in a few examples. But what this is telling us, what this equation and that set of equations is telling us, is that in the hydrostatic condition, right? So again, remember when there's no fluid motion, pressure is really just a function of the position relative to some known location. So if we know the pressure at some location, all we have to know is the delta C, change in height, between that known location and whatever other location we're trying to solve for pressure at. It doesn't matter, X and Y don't factor into this. PdX and Py are equal to 0. So X and Y are not really going to matter. The fluid properties also matter, right? So the density of the fluid matters. If you did this on Mars or something, you had a different value of G, that would matter. But really just this value of gamma is what matters. But again, in hydrostatic condition, the pressure doesn't depend on motion because there is no motion. Doesn't depend on X because the PdX is 0. Doesn't depend on Y, it's P Y. This is going to be the basis actually of a trick that we're going to use to solve manometer problems, or in general hydrostatic problems. So as an example, let's say that we have a swimming pool, like this design here shown on the right, filled with incompressible fluid, probably water. And we want to find the pressure at the bottom of the pool. So we're going to say that the pool is located in Salt Lake City, the height is 12 feet. And we want to find the pressure at the bottom of the pool in atmospheres, given that the atmospheric pressure in Salt Lake City, 0.85 atmospheres. How would I start this? What would I do? Let's say it's water. So I'm not just going to say incompressible fluid. We're going to specify that it's water. How do I get started here? What equation should we use to get started here? T2 minus P1 is minus gamma T2 minus P1, right? That's where it is. And we actually have this vector label, right? C1, C2, P1, P2 are labeled there. So we can start exactly at that point. So we start with the hydrostatic pressure distribution. P2 minus P1 is equal to minus gamma Z2 minus Z2. What is P1? Yeah, it's just the atmospheric pressure. Atmospheric pressure, right? P1 is just atmospheric pressure. Why is P1 not 1 atmosphere? What else? Right. So 1 atmosphere does not just refer to the ambient atmospheric pressure wherever you are. It's 14.7 pounds per square inch. It is a measure of pressure. So the atmospheric pressure here is not just 1 atmosphere, about 0.85 atmospheres. So P2 is the pressure at the bottom of the pool we're trying to solve for. That's going to be our unknown. What should we use for Z1 and Z2? So we know the height of the pool. The overall height of the pool is, we said 12 feet, right? Or the depth of the pool is 12 feet. So what do we use for Z2 or Z1? Yeah.
You just said Z1 and 0 instead of the reference.
And then would be 12. Would Z2 be 12? Negative 12. Yeah. So that's honestly where probably the most mistakes will happen. So again, if we set Z1 to be 0 as our reference, and that's pretty good, right? We know the pressure at 1, so we're going to set that as our reference Z. Remember that our gravity points down, right? So our Z direction, our Z coordinate points in the opposite direction of gravity conventions. And so Z1 is 0, Z2 is minus 12. Yeah, pay attention to your signs here. That's probably the number one place where I see mistakes. Okay, so let's so again, we're going to say P1 is P atmosphere. P2 is our unknown. And when we take our Z1 is 0 and Z2 is minus 12 feet, we plug that in. We have minus 12 feet here. We take gamma to be gamma water, look that up. And now we have this expression here for P2, 0.85 atmosphere minus the specific gravity of water, which is density of water times minus 12. We can resolve this here, and now is this equation dimensionally consistent? Yes or no? Okay. Raise it. Show of hands if you think this is dimensionally consistent. See some hands. Show of hands if you don't think this is dimensionally consistent. Okay. So dimensions are not units, right? So dimensions would mean when we say it's dimensionally consistent, what we're saying is that all the terms have dimensions of pressure, and that is correct. All of these terms have dimensions of pressure. right? P is pressure. Atmosphere, that's a unit of pressure. Pounds per square foot, that's also. So this is dimensionally homogeneous. The units are not, right? So the units here, right? And I think that's here. So the units are not consistent. So we have to do a units conversion on one or more of these terms in order to look at our answer. So this is a valid equation in terms of dimensional homogeneity. Where we haven't violated that. We're not trying to add a pressure to a length. Right? But it is, but we have to do some unit conversion. And so we'll do unit conversion. Right? We want to have our final answer in atmospheres. And when we multiply by converted factor between atmospheres and pounds per square foot, we'll have 1.2 atmospheres of pressure at the bottom of the. Did you expect this to be higher or lower than the ambient atmospheric pressure? Higher, right? So for example, if you dive into a pool, you would expect to feel higher pressure on your eardrums, or why a submarine has to be so strong to withstand the pressure that it experiences as it dives. And so this actually is a sort of a gut check on your answer. So we move down in the fluid and the pressure went up. That's good. That means we got the signs correct. You'll notice here that means we had two negative signs that canceled out. That pressure to increase when we got to the bottom. So initially you started the problem and you said T2 to 12 feet. When you get down here, you get something that is less than 0.85 atmospheres. Say, wait a second, I can't take it. Right. Pressure does not get lower as we get to the bottom of the swimming pool. And so I made a sign error someplace and then go back in. So final question, how would this be different at sea level? Right, so for our pool, we're in sea level, at sea level instead of in Salt Lake City. How would the pressure of the pool, at the bottom of the pool be different? Yeah.
It would be higher.
It would be higher for atmospheric pressure, right? So at sea level, even if we have a 12-foot pool, same amount of water on top of it, we now have more atmosphere on top of this. And therefore the overall pressure, the hydrostatic pressure, going to be caused by all of the fluid pushing down on us, regardless of the temperature, right? Whether it's air, water, or as we're seeing manometers, mercury or oil or whatever else. Yeah. Molasses. Is there a good video having to do with molasses?
There is like the molasses, the like tank of molasses that froze open and like people died in molasses flood.
Oh yeah, I don't have the video for that one. Maybe a little bit. All right. So since we're talking about atmospheric pressure a little bit here, we want to review what happens in gases. So we were considering what happens within a fluid where gamma is constant. So if we were to say that's the PdZ is minus gamma, our implicit assumption, which I'm not making explicit, was that gamma was constant with Z. But this is not true, for example, in the atmosphere, when we consider the full height of the atmosphere. So one way to approach this is to start with the ideal gas law. So PV is nRT, as written in the book. And so we can use it to solve for the pressure as rho on RT, R for the gas, T, gas constant T. And now if we, so we'll notice here that the density is a function of the pressure. And so we can put this into our expression, and we'll have PdZ end up with minus P over RT minus P. So another differential equation that we can solve, moderately more complicated if you have a pressure on both sides. So anybody who's looked at homework 1 or just remembers how to solve this, what do I do? I'm going to solve PdZ is minus P over RT times G. What do I do to solve this? Separate the variables to integrate, right? In this case, as long as the variables are separable, in this case, they definitely are, meaning I can pull them out, independent of one another. Then, yeah, we separate the variables and integrate. So in this case, we're going to be integrating dp over p and minus g over rt dt. Which I have here. Make sure I have everything. From condition 1 to 2, right? So from some 0.1 to some 0.2 instead. And notice in general, I've left T, the temperature, inside of this interval. Right? That's because in the atmosphere, the temperature tends to vary with T.
What's the upside down thing? Is it another symbol for?
Yeah, yeah, exactly. Yeah, universal gas constant. So we can integrate the left-hand side and get the natural log. It shows up on your homework as well. And now we have to deal with the right-hand side, right where we have this integral of T over T. The easiest assumption is to assume isothermal, right? Just to see what we could get. Doesn't necessarily match what we really see in the atmosphere, but it'll give us some idea of what happens here. And there we get P2 is P1 times exponential of this term here minus G, T2 minus V1 over RT1. But in general, we expect the temperature to decrease with increasing height within the atmosphere. When is that violated? When does temperature not decrease with increasing height? Happens in Salt Lake City. Inverted, right? In inversion, we have an inverted temperature profile, right? When we have a lot of snow on the ground. So the ordinary case is that the temperature of the atmosphere decreases with increasing altitude, and that allows the warmer, less dense air at the surface to mix, right, which helps clear out the valley. But when we have a temperature inversion, when we have a lot of snow on the ground, the temperature at the surface is lower than the temperature higher in the atmosphere, and that creates a stable layer that we can mix because the colder, denser air near the ground doesn't rise, sticks around, collects all the pollution, everything we create, and makes for those local weeks. Anyway, atmosphere is not external in general temperature decreases with elevation. But if we relax that assumption, so for example, we can assume that the temperature is linear with Z or with altitude. So T is T naught minus BZ. Then we'll end up with this expression here, which is what we would call the standard atmosphere. So this is what we typically expect for atmospheric pressure versus altitude. And again, violated during inversion, very close to the ground. But this is what we expect. And the US standard atmosphere is plotted here. So it's actually a set of different assumptions that come from a set of different assumptions about how temperature changes with altitude, basically some curve fit to typical measurements, where the lower part, the part of the ground, is given by this equation. But then there are two other parts as well, given in your textbook. And this is defined as the US standard atmosphere. And so if you need to know how atmospheric pressure changes with elevation or altitude in general, this is a good place to start. So, for example, for WEB, we get about 0.83 atmospheres.
What is B?
So B is a constant, right? So B is a constant that comes from curve fitting to measure values.
The PA, I'm assuming that's atmospheric pressure.
PA is, I believe that's atmospheric pressure at the reference elevation. Right. Yeah. So that one. Yes.
Is B a function of the material of the fluid, or is it a one
Yeah, so you get, in this case, what we're looking at is the curve into air in our atmosphere on Earth. Right, based on measurements made in the US, but you'd expect it to hold around. Yeah, this is very specific to atmosphere on Earth. So you would expect different values, you get all of those coefficients if we had different, right. So we run means, we have different standard atmosphere. Yes.
So is PA also gonna value in the table depending on the height?
No, PA is going to be this fixed out. I believe the PA is not 1.33, but it's not correct. Right.
So it's just that atmosphere pressure.
I believe, and again, if I'm wrong, I will. Any other questions? Okay, so yeah, so let's get to pressure of 28%, which is where I started from. This problem, approximately the day box. Okay, so now let's consider the case where we have multiple fluids stacked on top. We talked about this a little bit with air and water and swimming pool, but we can generalize this. So if we have multiple fluids, then we can add the pressure contributions of each layer. So for example, if I want to find the pressure down here at position 5, and I'm sitting under a layer of mercury, sounds pretty bad, but I'm sitting under a layer of mercury. And I can basically just add up the contributions, pressure contributions from each layer. And so we just work our way down from. So I know the pressure here, P1, atmospheric pressure, or whatever pressure it is, whatever ambient pressure it is. I can just work my way down through the layers. So I say, P2 minus P1 is minus gamma, T2 minus C1. Make sure I'm using the right gamma for this case oil. And then that would be P2. Now I want to find P3, so I'm going to mark my way down. P3 minus P2 minus rho W, right, so water times G, Z3 minus P2. Again, just mark my way down. P4 and then C5. So just going to solve these kind of problems sequentially, just adding up the pressure. So again, reminder, pressure goes up as we go down. So if you're looking at a problem like this, and you're starting to get a little bit confused on the negative signs and where the negative signs are, and you're getting an answer that you don't quite understand, it's just remember the pressure goes up as we go down. So you have as we move down within a fluid, the pressure should rise. This will become, I know I keep saying this, and it seems like this should be obvious. But when we start dealing with more complicated situations, right, like this, where we now have a fluid here, in some weird shaped tube, remind yourself, the pressure goes up as we move down. So, the pressure at this point 1, right here, is it higher or lower than the pressure at this point here? Higher. Right, it's higher. So the pressure increases as you move down from the fluid. But now remember the other thing that we said was that in the hydrostatic condition, we're assuming this is at rest. So in the hydrostatic condition, the dP dx and dP dy are both equal to 0. So no gradient in pressure with respect to x or y. And so one consequence of that is that we can jump across as long as we're within the same fluid and it's fully connected, full path to move from one point to another. If these 2 points are within the same fluid and at the same elevation, same C, we can say that the pressure here is equal to the pressure here. So if I would ask, so if we want to solve for the pressure at this point within this fluid. We can find the pressure here, we jump. And that's kind of the trick, solving these problems. So we can make horizontal jumps within the same thing. So in this case, let's say that, I want to find the pressure within this bulb. So let's say I have this manometer here. I have some gas that's separated by a liquid from atmospheric condition. And I want to find the pressure within this bulb, right? So the pressure at this elevation is CA. So I can solve for this using my delta P is minus gamma delta C expression. We're just applying it sequentially. So let's say we start within this fluid 1. Okay, so we're gonna start with this thing, this unknown PA that I want to know. We would say that PA minus P1 is minus gamma 1, but this is my fluid 1. Some gas. You know, maybe it's some toxic or caustic gas that I want to keep isolated from the air that I'm breathing. So I can do this. Use this kind of trick. Minus gamma 1 ZA minus Z1. So I have PA plus gamma 1 CA minus Z1 is equal to P1. So now, question for you: is P1 higher or lower than PA? P1, is it higher or lower than PA? Higher. Again. So here I can solve for PA in terms of that P1. And then now if I move over to fluid 2, I have my atmospheric pressure. This is the pressure at the top of this fluid column here. I'll say P atmosphere is going to be approximate. So my P2, the pressure at the top of this fluid column, is going to be approximate P atmosphere. Basically, this is like assuming that the density of whatever I put in here is much higher than the density of whatever in the atmosphere. So this small difference in elevation matters. If for example, this is air, this is water, this small this is. So Z2 is about PA. And now I'm going to jump across and say that the pressure 1 here is pressure at the same elevation within this fluid. So P atmosphere minus P1 minus gamma 2 Z2 minus Z1. And now I have this expression. And now I can put this all together and solve for PA, right, in terms of all of my other variables. Right, so I can find the pressure within this bulb as a function of my atmospheric pressure, my gamma 1, my gamma 2, and my elevations.
Are we essentially ignoring the entire bottom section?
Yeah, I mean, so yeah, so the question is, are we essentially ignoring the bottom segment? And we kind of are, right? We're saying that. So yeah, one consequence would be it doesn't really matter how big we make this bottom section, right? Because we're jumping across horizontally. So yeah, the height, the depth of this bottom. So one thing you might see, I think that happens in any of the problems in the textbook, but the you know, so for example, if you're given another elevation down here, right, the value of that is not active in 0. Because again, just jumping across. Yeah.
I get what you're saying, and it makes sense, but I'm just imagining, like, what if it's like 100 miles long or something? And does it still not matter how long it is?
In the static condition, it doesn't matter how long. Yeah. Yeah, I mean, at that point, it's you have to consider like curvature of the earth to figure out your elevation, right? So is it 100 miles long and completely flat, or they're not long, following curvature of the earth or something. But yeah.
Yeah.
And we'll see some consequences of this, some interesting consequences of this, non-intuitive consequences of this in a video on Friday. How to do the shape of containers. Earlier in the class. All right, so this is a relatively simple manometer problem, but we can use the same principle to solve things like this. And you'll get a problem that looks just like this on your homework, if not exactly this. And so we can use the same, but again, I want to emphasize, really just go step. Move your way stepwise through the problem. Do these problems in the problem. Okay, start taking shortcuts. And say, well, delta C is 12 feet. You know, just plugging that in. Instead of saying, okay, D1 is 0, so D2 is minus 12. That's when you run into trouble with these kind of problems. Depending on the identities of fluid and so on, it's not immediately obvious. For example, how PA and PB are going to be related. So we can't say that PB is definitely less than PA because we're not within the same fluid. There's no connected path in the same. So we really have to solve this going all the way across. We can say that P1 is greater than PA. P1 is greater than P2. So on all the way. P3 is greater than P2, and P3 is greater than P. Say that. But to find the relationship between PA and PB, so that we're working with the whole problem.
Despite the fact that P3 is lower than like P1, we still don't know if it's at a higher pressure.
Because we don't know the specific gravity. You're at the state of the specific gravity. Okay. Any questions on manometers? So, work methodically. That's my number one. Work methodically underway as you're working through these problems. And even though we've assumed a static condition, this concept of gravitational forces giving rise to pressures in fluids, this will come up as we move into more complex flows and we're considering motion. So this is the concept that we'll see when we're solving for example, we might ask, or our question was on a previous exam, you'll see as one of your homeworks. We'll be looking at draining liquid from a tank. Actually, so on one of the a midterm problem from last year was looking at after we've done some batch biodiesel production, you end up with layers of fluid within your batch processing tank. And if you're now trying to pour off the biodiesel that you produce, and you want to figure out what the flow rate is as that biodiesel is coming out, you now need to know the pressure at the bottom of the tank where your opening is, where your valve is. And that pressure at the bottom of the tank depends on the weight of the fluid column, of all the fluids above, right above that point. And in this case, it's multiple fluids. So we will be using this kind of concept to solve problems later on. Let's work through a while, so work through it methodically on the homework now. So an example is mercury. Another example here is a mercury barometer. It's just a good tool to be aware of. If we take a tube, we fill it up with mercury, and we flip it over into a pool of mercury. So take a tube initially completely full of mercury. Please don't do this. Please do not propose to do this for your capstone. We do occasionally get people proposing to use mercury for capstone projects as an absolute no, all the time. Yeah, please don't do it. But I think I have a video that demonstrates mercury barometers when someone did do this, so you don't have. So we take a tube though, filled entirely with the mercury in our minds only, and we flip it over into a pool of liquid mercury. Then, what will happen is, we'll end up with something like this, we're actually have some evacuated space, up top. And, what's happening here is that the pressure of the atmosphere, the pressure of the atmosphere, pushing down on this pool of mercury, supporting this column of mercury. And so from the height of this column, and knowing the density of mercury, we can figure out the atmosphere. So this is a standard device, old school standard device, to measure atmospheric mercury barometer. It's why atmospheric pressure is generally expressed in something like millimeters or inches of mercury. Height of mercury. That's referring to the height of the mercury column in the device. But we can use what we've learned to understand how this kind of thing works, right? So within this column of mercury is the pressure. How does the pressure down here relate to the pressure up here? Down here, higher or lower? Higher, right? Because we're down. The pressure here. What is the pressure at this point, right? Atmospheric pressure. Right? So as we're moving up in this column, the pressure is getting lower and lower. And what we have up top is basically that. So the pressure there is about zero. To show it's about zero, it's really the vapor pressure. But that happens to be very, very low. So a question for you all, before we break for today and finish our discussion of chapter 2. Oh, questions? Yes, yes.
I was just, with the other image, what's the difference between that and the capillary action?
Yeah, so what's the difference between this and the capillary action?
Like, can we measure the atmospheric pressure using water?
It's actually going to be exactly my next question, is why don't we use water?
Oh,
Which is a great transition. Why don't we start there and see, and then we can come back and see if that's okay. So, yeah, so my next question is why mercury? So why do we traditionally use mercury, which is very toxic within barometers? Yeah, but
Has a very low surface tension.
has a very low surface tension, which is one reason, right? So, so not going to have much of a capillary force, although we can get around that by making the radius of the water if we want to, right? So that doesn't necessarily tell us why we wouldn't use water. But that's part of the answer is if we make it too big enough, then we can ignore that surface tension. Yeah, which is going to be really dense, so you don't need as much. It's really dense, so you don't need as much. That's the biggest part of why we use.
so the change in the height does not depend at all when you're with the water sample, did not depend at all on the atmospheric pressure.
So in the water example, remember we had atmospheric pressure on both sides. This is a good question. Yeah. So in the water example, we had atmospheric pressure on both sides. We had the back. So imagine we cut open the top of the tube, right? So if we cut open the top of the tube, then we have atmospheric pressure pushing down on the fluid both in the column and within the and in the case of essentially no surface tension for a large cylinder, so we don't have any appreciable surface tension, then the then this would just be the height of the fluid.
If we were to use water, but like somehow create a vacuum at the top, would it be the same as if we use mercury? Give me the same height?
So this gets to the other issue, which is that vapor pressure of water is not about zero. So another reason why we use mercury is that vapor pressure is very low. And so we can basically assume that the pressure at the top is roughly zero. So in water, we would have to say the pressure at the top is not zero, or more than water at the top. We're going to end up with some pressure there, just depend on other conditions, rather temperature.
Could you like connect some valve or something? I don't really know how it works, like create a vacuum at the top. Well, would that work? Wouldn't you be swimming?
Yeah, you'd be boiling the water. You experienced the you just boil the water. You're wrong. But related to the density, so we would do this with water. So another reason why I did here, Robert. 34 feet. Yeah, so that's why we use. All right, thank you all, see you all on Friday.